So our second session, we're going to talk about increased shaking, and in particular, the implications of Canada's 6th generation seismic hazard model. Michael Collage is going to chair and guide the session today, and is certainly the expert. He was kind enough to give an ICLR webinar just on this topic earlier last year. So if you did not see our January Friday forum session, it is available to anybody who'd like to follow up on Michael's work talking about the model itself. But he's going to lead a conversation here with Tegan, Emil, Arash, and David today. We have a number of slides in this session, and Michael's going to work really hard to keep on schedule as he guides us through the conversation. And I'm going to turn it over now to Michael.
Thank you very much, Paul. Yeah, so as Paul mentioned, the goal of this session is to, so just introduce myself. As Paul mentioned, I'm a seismologist with Natural Resources Canada, and I'm working principally on our seismic hazard estimates. And the goal of this session is to kind of give an overview of some of the considerations and aspects for the estimate of hazard and risk in Canada, and some perspective by the various vendors and organizations here on some of the new science that has come out on hazard estimates in Canada. So go ahead, Paul, we can move slides. Right, so the 6th generation seismic hazard model developed by Natural Resource Canada, we released this in 2020. And the files associated with this and some of the documentation is available on the Earthquakes Canada website and on the Natural Resources Canada website for people that are interested in more information. And the model is currently proposed for inclusion within the 2020 edition of the National Building Code of Canada, which is slightly delayed and is expected to be released this year in 2021. And the map I'm kind of showing here is a map that shows the change in our estimate of hazard between our previous model released in 2015 and our most recent model being the 6th generation model for a short period hazard estimate on firm ground. And I mentioned that because in a hazard model, just like in a risk model, you know, there are hundreds of products that are made, and this is just one that we're showing here. It's admittedly one of the more relevant ones, but the particular changes in a particular location would depend on the full suite of hazard products. And for each of these triangles here is kind of a city, and the color indicates the percentage difference in hazard for this particular variable. You know, and if we look, you know, in Western Canada, in particular southwestern British Columbia, you know, we see that hazard has increased, you know, on the orders of 10% even to, you know, 40% and higher. If we look at Eastern Canada, we see that the colors are redder, indicating higher changes. I will note that the absolute levels of hazard are typically lower. So even though the relative changes are higher relative to the previous estimate, many of the absolute values are of course lower than in southwestern British Columbia. And just wanted to set the stage for our session today. You know, this is some of the new work that's come up by us. And we'll start off by just talking about the general approach that all the vendors and organizations do to estimate hazard and risk in Canada. And with that, Paul, we can go to the next slide. Yeah, and the next one after that. Yeah, so Tegan will get us started.
Hey, okay. So yeah, I guess we're sort of going back to the same ideas that I already talked about, but now maybe going into just a little bit more detail about our specific seismic approach that we take. So as Michael's introduced, we're using this NRCan hazard model. So as I mentioned before, we have all of these different seismic source regions with a certain magnitude frequency distribution that's you know, directly generated from our best understanding of the seismicity here in Canada, both in terms of observed seismicity, historical seismicity, and some recent paleoseismic work that's helping to kind of elucidate these faults that we may have no memory of experiencing, but have ruptured sometime in the last 12,000 years. So from there, we take those ground motion prediction equations that I was talking about. So in this case, some of the updates that I'm sure we're going to talk about are things like the incorporation of the NGA East model. So that's for Eastern North America, thinking about how the shaking is experienced from earthquakes in that region. And then we kind of take that hazard model that says, where do we expect shaking to occur, with what probability and what intensity? And then to think about the risk, we're gonna kind of take the overlap between that and our exposure and our fragility. So again, topics we've sort of been talking about throughout this half-day session so far. And I'll kind of just maybe speak to a little bit more specifically. So if we can go to the next slide. For our NRCan risk model that we produce, what I'm showing up in the top left here is thinking about is showing the ground motion prediction equations that are used in the NRCan hazard model. So you can see that we've got our different tectonic regimes. We've got our stable shallow crust, so that's going to be most of our eastern Canada. We have active shallow crust, so that would be in places like British Columbia if we have shallow earthquakes. We've got our subduction interface, so the Cascadia subduction zone in Western Canada and the Western United States, and then subduction intraslab. So as I said before, that's where the subducting slab is being pulled down into the Earth's mantle, and that tension is causing earthquakes in the subducting slab itself. And so you can see that we take all of these models, and they're each assigned a sort of different weighting, so that we can look at the suite of all of these different kind of modern and state-of-the-art. We can sort of take into account these new models as they're created without needing to put 100% weighting in any one of them. So that's sort of touching back on that topic of how do we update these models. From there, as I kind of touched on before also, on the right-hand side, I'm showing a map of the VS30 values. So that's the shear wave velocity averaged over the top 30 meters of the soil. And so this is kind of a proxy for how does your specific site behave in earthquake shaking. So if you're on hard rock, you're going to tend to have experienced the kind of minimum shaking that's arriving to your location. Whereas if you tend to be sitting on maybe a thick packet of soils, then you're going to have some amplification of that shaking. So in this case for Canada, we use a model that's based on the topographic slope. So the steeper, we can use the steepness of the land to sort of figure out what is the likely shear wave velocity. And that's based on some work by our colleagues at the USGS. And then on the bottom left there, I'm showing an example of a fragility function. So as I mentioned before, we're using fragility functions that are based on HAZIS and were updated by the Global Earthquake Model Foundation for Canada. And so you can see here that we just can look at what's the probability of landing in a certain damage state given the amount of shaking that you're observing at your site. If you go to the next slide, please. So the final thing to consider is our exposure model. So at NRCan, we had to develop our own exposure model, a work that's been going on over several years and led by Marie Journet. So in order to get kind of uniform coverage across the country, the whole process starts with some satellite remote sensing. So in the top left there, that kind of cascading figure. So from satellite remote sensing, we're able to determine the areas of Canada which are settled. That's our settled area map. And from there, we can infer a land use type. Once we start to fold in some of our census data from Statistics Canada, then we can create a representative building portfolio where we say, you know, if this is a urban high density region, then these are the kinds of building typologies we expect to see there. If it's low density, mid density, maybe it's industrial commercial, or maybe it's a rural area. And we can also include information from StatsCan about our social fabric. So that's thinking about our demographics, things that will be important for earthquake resilience. Things like, do we have people who speak one of the two official languages so that they'll be able to get information in the event of an earthquake? Do we have folks who are maybe housing stressed or don't have secure income from their work? Those are the kinds of things we can consider there. And it's important to note when I'm talking about this kind of portfolio of buildings, because this work is based on the HAZIS taxonomies. So we're still using mostly the same taxonomies that were introduced there. I think there's something like 32 of them. And we have a couple of new ones that are being introduced for wood construction in Canada, because so much of our construction is wood. And there were some certain construction practices that tended to happen here in BC that are a little bit more nuanced in terms of their response to shaking. And then on the right-hand side, the other kind of factor we have to consider for this exposure model is the vintage of our construction. So here we have an approach where we take the approximate year of construction of the building and the approximate seismic design level. So if you live in Victoria, you have a higher seismic hazard, and therefore when your building was constructed, if there was any building code, it would have been designed to a higher level than that same building in Saskatoon. So we can take into account both the age and the region it was located in to assign a certain design code. I think next slide, or is that my last slide? Oh, okay. So yeah, all of this to say, we're able to produce a risk model where we can look at kind of the whole country. We can also, of course, break that down into smaller regions. We can specify by certain, building typologies and say, let's look at all of our concrete high-rise, or we can look at our occupancy types. Let's say we want to look at all of our agricultural structures or all of our residential buildings. And we can also think about different retrofit strategies, which I think is kind of unique with our model. So we can say, if we took every building in Canada and bumped it up by 2 levels of design code. So if it was a building from, 1972, let's say, well, what if we were to imply some, advanced retrofitting techniques and bring it up to as though it were built in, 92 instead? What would be the difference? And so from that, it's a little, got a little funky there with the collection of slides, but what I'm trying to show here is that generally speaking, when we're looking at some of these ground up losses and our return period, the x-axis is totally gone, but the spot that we're highlighting here is our 500-year return period, or 475. And we tend to see about a $40 billion loss, and that's with the new 6th generation of hazard model from our colleagues in Ottawa. So that's kind of the one of the really important metrics that we look at specifically as the NRCan risk model, because that's sort of the value that, as we've talked about already today, insurance companies, you're regulated to prove solvency for that 1 in 500-year event. And we can see there that with some formatting issues, most of that is borne out by British Columbia, but with a sizable contribution from both Quebec and Ontario. So with that, I think I'll turn it over.
Again, thanks, Tegan. Paul, if you could advance to the next slide. Thanks. So yeah, I'll start with talking about a little bit on the overview of our model first. This is the framework or the flowchart of all of our catastrophe models. We use an event-based catalog to represent the hazard. So this uses a stochastically generated catalog of all scientifically plausible events. And that's combined with the information about how ground motion, in this case, ground motion models are used, provide information of the intensity at different locations. And then by looking at the exposure and then the engineering component that basically translates the hazard at the location of exposure, then we get to the estimate of damage and financial losses. Next slide, please. So our Canada earthquake model was last updated in 2017. And in order to provide a more comprehensive view of seismic risk, in addition to shake, we explicitly account for liquefaction, landslide, fire following, and tsunami in our model. And the model covers all lines of business and all coverages, which is building, content, and business interruption. And in addition to regular building types, we also support for industrial facilities, infrastructure, and some specialty risks. And in all generally in making sure the model is working fine and to do the validation and calibration, we look and use a very high resolution industry exposure database, which is collected by getting information from public and private sectors. Next slide, please. Yeah, so on the hazard component, I'll start with that. As I mentioned before, we provide a seismicity model that covers both US and Canada. So it's a uniform seismicity hazard for both of the two countries. And in developing the hazard component, we then look at information from both sides. We incorporate the data and information from historical catalog and seismic zones and all the information from both GSC and NRCan, and also from USGS information. And then we supplement that with some of our own in-house studies. For example, in the Cascadia region, we do kinematic models for the cross-star rate. And in order to then provide the hazard module, we use a 10,000K simulation, both time dependent and time independent. And time dependency is actually very important in the western part on the Cascadia subduction zone. And in order to provide ground motion models properly, we use a combination of ground motion models in a logic tree approach, and then use weighted average to properly represent it. And then in many places, it's very, very important to account for liquefaction. This is, for example, in the areas of Fraser River and in the east in the St. Lawrence River. And we include that by accounting for high resolution information of soil and groundwater data, and also basin impact in the Western Canada. And at the end, we have this model peer reviewed on our catalog, on the hazard side with the Canadian expert. In addition to our stochastic catalog, also to better capture the tail risk, we incorporate some deterministic scenarios that represent very extreme disaster scenarios for either from very old historical events or from some plausible events that can happen, for example, in the Eastern Canada. Next slide, please. Now, when we talk about the vulnerability, one of the challenges that we have in the vulnerability is that there hasn't been really any major damaging earthquake, fortunately, in Canada. But from an engineering perspective, this really poses a challenge because we don't have a lot of data on to validate our vulnerability model to those local data. So our approach to overcome this challenge is to utilize a hybrid approach in which we combine our engineering analysis. We use a lot of engineering models and combine it with the data from other parts of the world that are relevant and similar to in nature to Canadian data. And by combination of that, we develop vulnerability function for different types of buildings. We, for example, identify and differentiate buildings by height so that we can have different intensity measure to represent their damage functions. And also similar to what Tegan mentioned, it's very important to look at the building codes. Building codes really define and dictate how buildings behave, provided that they are properly enforced. So we look at the evolution of the NBCC code from the beginning until the latest one, and that allows us to capture how vulnerability changes spatially and temporally. So for buildings that are built in different parts of Canada with different years of construction. And in doing so, again, in having our vulnerability component validated, we work closely with experts from Canada, both in collaboration and for peer review. And yep, with that, I'll turn it to the next presenter.
Thanks, Arash. I hope you can hear me well. Next slide, please. RMS Canada Earthquake Model lives within RMS North America Earthquake Model, which we released in 2017. In Canada, as you can see on the right-hand side map, RMS model has a full geographical coverage of all 10 Canadian provinces, and also including the 3 Canadian territories. So when we look at the latest scientific understanding of the seismic hazard and including risk, it includes a complete view of seismic risk, which is a forward-looking model, and I will detail it in the next slides. So as the models come with the uncertainty, we understand that, especially if there's lack of data, differentiating the regional variations becomes key. So the RMS model is actually validated all these aspects through the historical event loss and probabilistic seismic hazard analysis on both large scale and the location level. These details are also documented and published for our clients. Last but not least, we work very closely and collaborate with the scientific agencies. And going further, we publish journal publications to improve the modeling capabilities for the scientific community. Next slide, please, Paul. So in the previous slide, we were looking at the RMS model from 30,000 feet above. Let's have a closer look in the earthquake framework for the CAT modeling. Our goal is to build models that can actually stay valid for many years, anticipating the scientific advances which may be published after the model release. This is exactly what we had in mind while we were building our model back in 2017. Looking at the source model in the earthquake rupture forecast and stochastic event set module extends the Cascadia subduction zone farther up north to reflect the actual extent plate boundary. which is very important. It has the time dependence on the subduction interface, adds this chief earthquake catalog to supplement the historical event catalog, and has a very careful treatment of Charlevoix seismic zone. And we will talk about this in the later sections. Next one. RMS model also incorporated the most of the latest ground motion models that are published in NRCan 6, that are NGOS 2 models, BC Hydro or Abramson et al., 2016 preliminary NGA East models across Canada. We also allow the users to stress test loss variations informed by the model epistemic uncertainty or model-to-model variability of the ground motions and the vulnerability. Turning on the site conditions, which is very significant, will activate the high-resolution site amplification models for you. And we also developed an explicit sedimentary basin model in Vancouver. Next, please. Our site response models actually use the underlying RMS high-resolution geology-based data, VS30, explicitly. And we also developed groundwater depth data layer to be used in our probabilistic liquefaction model. And we also developed a probabilistic landslide model. So up to now, I was really focusing on the seismic hazard components. For seismic risk, of course, we need the vulnerability module. Next, please. The model features 6 vulnerability regions for Canada. This is all to better capture the regional differences in design and construction practices, and also reflect the higher seismic design levels in, let's say, Western Canada, Southern Quebec, Ontario, and the Maritimes. We work with the local experts as well to understand the local construction practices and the building code design practices. So in addition, there are 3 business interruption regions, and building inventory distribution varies by location and the lines of business, which is important actually to predict the likely building characteristics when the user does not specify them, of course. So aside from the shake model, next please, RMS model includes tsunami accumulation footprints for the damage, especially due to the Cascadia subduction zone events, fire following, and sprinkler leakage modeling across Canada. And if you're interested, of course, in learning more, please contact Brian about this. Thank you very much.
If we go to the next slide, please. Thank you. My peers today have covered this off, but just to reiterate, we have seismic risk, which is the whole enchilada, the hazard, the vulnerability, and the financial modeling combined to create loss outputs on a probabilistic basis. So working backwards from right to left, we've touched on the financial model in the previous section. For vulnerability, we incorporate engineering studies and simulations. And as an example, we've introduced 3D vulnerability functions for low-rise timber homes in particular, where we define the vulnerability curve for these structures by using multiple hazard parameters, so multiple spectral acceleration periods. I think it was Tegan or someone mentioned earlier the high proportion of timber homes in Canada, and sort of it's a large risk there. We also have 7 vulnerability regions, the vulnerability categories that conform to the National Building Code for Canada, and actually as it has evolved over time. While there are been limited events in North America to assess actual claims damage, CoreLogic have been on over 90 post-earthquake site studies around the globe, and we collect claims data, insurance claims data where available. And this includes sort of major earthquakes over the last 30 years. So we combine engineering analysis, simulations, and this research together to inform our vulnerability. And we do this to address our main issue is equating building damage, so typically a damage ratio of 5%. What does that actually mean in terms of repair cost? I think that's a big fundamental gap to connect the property data analytics with our CAT models. And that's fundamentally sort of what matters to insurance clients, in my opinion. So there are also the secondary perils that are included in the CoreLogic model, such as fire following, sprinkler leakage, and of course, liquefaction and landslide explicitly modeled. The next session will cover fire following in more depth. But again, if we just take a magnitude 9 Cascadia event as an infamous, famous example, the losses from these secondary perils can easily add 20 to 30% or even more on top of the shake-only loss. Again, even more depending on the portfolio locations, etc., in an insurance book. And then we have the hazard component, the two sections on the left, which given the 6th gen NRCan update deserves more focus today. So when talking about the hazard components, these both include both the hazard definition. So this is creating the event set of what could happen, the where, the how big, the how frequent. And again, we've discussed the different seismic sources of what can happen. And then we need to describe the propagation of the hazard to a site. So these are captured in ground motion models and how we factor local soils on the simulated ground motions. So the current CoreLogic Canada quake model is a hybrid of NRCan models, 5th gen and 4th, our own research, and across the border to the USGS National Seismic Hazard Models of 2008 and 2014. So it's probably not the most attractive to describe it as a Frankenstein's monster of sorts, an amalgamation, but to date, we've cherry-picked the items that we believe add to capturing the uncertainty, where we evaluate the risk during each of the updates. And we have some considerable departures from 5th gen NRC in our model. In walking through the CoreLogic hazard model, we do capture multiple weighted ground motions, capturing the median and the sigma, just like the update in the 6th gen NRCan model. However, currently we do not incorporate the newly introduced GMM for the NGA East. So NRCan gives a 50% weighting for Eastern Canada for this, as I think it was Tegan showed in an earlier slide. If I had to pick the single largest change in the latest NRCan seismic model in terms of impact that would probably affect the CoreLogic model, that would be my go-to, the NGA East equation update. So more change may be underfoot as these preliminary results are further analyzed in years to come. Thanks.
Thanks. So moving along, we're going to talk about some of the considerations for estimating hazard risk in Western Canada, and specifically some of the expected impacts of some of the recent results that we shared in the NRCan model. And I just encourage the panelists to be conscious of their kind of allotted time for their sections. So if we go to the next slide, Paul. So very briefly, Paul mentioned, today is the 321st anniversary of the Cascadia 1700 about magnitude 9 earthquake. As we're all familiar, southwestern British Columbia is in the zone of active plate tectonics, where we can have earthquakes, large earthquakes of different styles occurring in specifically being, some of these large megathrust earthquakes, but we can also get earthquakes such as the Nisqually earthquake, which occur in the in the slab that's underwriting the North American plate, or also in the overriding plate, and these can equally cause damages as they can be closer to population densities. And on the figure on the right here, this is for earthquake planning scenarios. It's what we call a shake map, which just shows some of the expected perceived shaking or intensity from a large earthquake, such as here being demonstrated a magnitude 9.3 Cascadia event. And in this session, we'll hear some of the perspective from the panelists on estimating risk in Western Canada. And can you go to the next slide, Paul?
Can you advance the slide, please? Thank you. So an issue in understanding the impact of the 6th gen NRCan view of risk on the CoreLogic model is difficult. As I mentioned, our starting point for our current model isn't a pure implementation of NRCan's 5th gen NSM. Sorry, too many acronyms. So to recap the changes at a very high level in the latest version of the Canada seismic hazard model, Michael's map at the start had a map of Canada with triangles earlier, showed a large swathe of increased hazard around large areas of around up to 25 to 50% across BC, including Vancouver in particular. I believe this map was at the 2% in 50 years. Michael, please correct me if I'm keep me honest there. So these changes are due to multiple things, incorporating sigma in the ground motion models and change in the treatment of the Cascadia and in-slab sources. So where the, and of course, a higher increase in hazard is observed around Victoria with the additions of the active faults in the Leech River Valley. So in the CoreLogic model, we have cross-border consistency with US and Canada, This is to provide consistency to clients with exposure north and south of the border. And to maintain this consistency, we currently use the USGS treatment of the Cascadia in our model. There's also an overlap in seismicity close to the borders that affects large areas of risk, particularly in Quebec. So particularly for Quebec, this makes it harder to work out the impacts of the latest NRCan model or update on any CoreLogic Canada quake model update. Of course, Michael mentioned the big one, Cascadia event, and it's typically assumed to drive the majority of risk in Quebec and Western Canada, but actually by how much? A key thing we must remember is that seismic sources do not drive financial return period losses equally. So if we can go to the next slide. What I'm showing here is I've run our IED, our industry exposure database. So this is CoreLogic's view of the insurable asset base in Western Canada. And I've normalized the losses against what seismic sources are driving the losses at AAL and each TVAR return period. So we're just looking at ground up damage level here to keep this simple. Of course, we could do this exercise on client books at the gross loss level to see what's actually driving insured losses. But when we look at indicative changes, I've combined subduction, intra and interslab contributions here into Cascadia, but we could split that out given time, etc. So for instance, starting on the left at the AAL, the average annual loss, we can see the biggest seismic driver of the AAL is actually the background. That should be background seismicity, the darker green color. And the Cascadia drives only around a third of our AAL risk, sorry. Whereas we move out into the tail, especially maybe the top layers of what we focus on in insurance, covering the 1 in 250, 1 in 500 year return period, then we can really start seeing that the Cascadia is driving over 2/3 of this area of the curve. So just as an example, in a CoreLogic model update, we can see that any updates that are purely to subduction zones would have a larger impact on the tail risk of our insurance clients on an insurance basis. Whereas any updates to background sources would affect essentially the AALs or the location level pricing metrics that typically our clients use. And we can see the active shallow crust source is actually not driving an awful lot compared to the other two. Given my time, I'm going to stop there actually. Thank you.
Thank you, David. Next, please. So most of the earthquakes occur along the active plate boundaries, as we know, and 60% of the Canada's earthquakes occur along the British Columbia coast, which is mostly impacted by the Cascadia subduction zone. And therefore, I want to focus on how well defined the EP tail of RMS Canada earthquake model is. Next, please. So the top bar charts are showing what type of events or source type contribute to the 500-year return period loss per magnitude bin on the x-axis. For example, the largest contribution is coming from the magnitude 7 to 7.5 bin by the intraslab events in the dark blue and the background ones. And you look at the interface events on the Cascadia subduction zone beyond 8 plus magnitudes, you can see that's the major contributor for larger magnitudes. Next, please. When we look at the bottom plot, colors now change the recurrence instead of the source type. Recurrence is something like the event frequency or how often a single earthquake occurs. The yellow color or greenish color shows here the frequency in the order of few thousand years. The turquoise means these events can occur on the scale of hundreds of thousands of years. And we find that most of the interface events in the magnitude bins 8 plus will have frequencies lower than 10,000 years. So for the magnitude ranges between 6 and 8, basically the event frequencies are in the order of tens of thousands to hundreds of thousands of years. The total number of events, when you look at it within that magnitude, kind of reaching to 12,000. So this illustrates that an accurate representation of tail risk actually requires event recurrences that reach beyond a few 10,000 years. Next, please. On top of that, I mentioned on the right-hand side bullet points in my previous slides, but another important aspect is that our seismic hazard model is more detailed than NRCan 5, and it's much similar to NRCan 6 with additional capabilities. As I mentioned before, given the RMS ground shaking logic tree, which is a weighted average of individual suite of ground motions, is forward-looking and more similar to NRCan 6 than 5. Next, please. So now let's focus on actually the Fraser River Delta in British Columbia. That's another important part here. It has three drivers of liquefaction hazard: the shallow groundwater, loose sandy soil, and a web of river channels. This model is shaped actually by the lessons learned from Christchurch event sequences from the New Zealand. So this map on the right is showing us the liquefaction contribution to average annual loss, AAL, and the dark red colors are showing the higher contributions. Another key differentiator in RMS model that I would like to mention, next please, the Vancouver Basin. It's developed by an in-house study using the site response simulations. There's a high exposure, high infrastructure on top of the deep and softer sediments in this region, which makes it really important. And the map on the right shows the basin extent and the fundamental period of the soil as developed by RMS. So the red colors mean the deep sediment thickness associated with the longer periods. For example, next please. If your portfolio has a tall building at location 1, including the Vancouver downtown, for example, then it will experience a much amplified ground shaking due to the resonant basin effects. But if you look at number 2, next please, then you would be having more impact from the shallower sediment thickness impact on the shorter buildings. So this is not included in NRCan 5 or 6. So RMS model will result in more granular loss variability in this region. And you can read our blog on these topics as well. Next please. Thank you very much.
Thank you very much. So in this section, I'm going to talk about how we model different parts of different types of events in the Western Canada. Could you go to the next slide, please? Yeah, so Michael and other presenter already mentioned that there are 3 different types of earthquake in here. And I'm going to talk how we model each section in our model. Now, starting from the Cascadia subduction interface, as I mentioned, our model was developed last in 2017, so that's before the 6th generation. And we also looked at it from a combination of a forward-looking approach by combining different data sets. It is based on the 2012 Goldfinger model that is also used in the USGS, and it does account for the entire full rupture of the Cascadia with different probabilities to different magnitudes, and also considers large magnitudes of 9.3. Now, in addition to the full rupture, we also take into account the possibility and probability of having partial ruptures. That's mainly in the southern part of Cascadia, and mainly impacting the US side of the border. Now, another thing that is very important in the Cascadia subduction zone is the time dependency. As we spoke already, the last time the events ruptured in full was about more than 300 years ago. So the time dependence and time independence becomes pretty different, and inclusion of dependency is very, very important. Now, the second type of earthquakes that can happen here, in-slab deep earthquakes. And as you heard from Michael's presentation and publication by NRCan, one of the big changes that have been done here in 6th generation is that compared to the 5th generation, which only considered a single depth and a single geometry, 6th generation considers a multiple depth and geometries. And that's exactly what we have done in AIR. We have modeled the depth here with the varying depth that follows the slab geometry and depth model from USGS. Next slide, please. Yeah, and on the crustal events, we model this crustal events using information from faults, and we also account for aerial seismic zones. In order to properly model the seismicity and faults, we actually incorporated a lot of different database of faults. This includes the database of faults from inside Canada, and also from Western Canada and Western US and Alaska. Concentrated and focused on the lower mainland in around Vancouver area, for example. We do account for the Devil Mountain fault, and we also include the faults that were presented by USGS in the Seattle and Tacoma that actually have very notable impact in the Vancouver area. And that's added with inclusion of this background seismicity models that allows for having magnitudes of up to even 8 in areas that are not necessarily associated to faults. And our seismicity rates primarily use historical data and fault data to construct magnitude rates, but we also go beyond that, and we have used kinematic models that we developed in collaboration with experts in this field that uses GPS and geodetic data to better calculate and capture the strain rates for these crustal events. Next slide, please. I think we don't have, okay, it's looking a little bit different. But anyways, this is about the ground motion modeling. And as we heard, one of the changes again in 6th generation is the approach that is not using a representative suit anymore and rather uses a logic tree with a weighting function. And that's again exactly what we have been doing in all of our earthquake models. We include information from VS30 directly into our models to better capture the amplification and the uncertainty. And more importantly, as you heard from Emil, this region in the Western Canada is really impacted by the existence of the Georgia Basin and the liquefaction. Georgia Basin is something that typical amplification functions are not showing it. So including that is very, very important, especially for the tall buildings. And that's including the liquefaction is explicitly accounted in our model. And next slide, So in general, as I wanted to say is that our model is not exactly the same as 5th generation. It uses data and information beyond that. And with the change that we have seen from the 6th generation, we actually feel that the two models are actually getting even closer than before. Thanks.
Hey, so you can go to the next slide. So generally speaking, the NRCan risk model is pulling the NRCan hazard model. We use a simplified version of this where instead of sampling the entire logic tree, we have a version that Michael and our colleagues in Ottawa have kind of used expert judgment and some testing to trim the logic tree in such a way that we're not affecting the mean hazard, but it makes the risk assessment for the entire country computationally tractable. So we know that our simplified our simplified hazard that we're using in our risk calculation is consistent with the NRCan hazard model to usually within 1 to 3%. And so we have this kind of validated hazard model, and that's going to be for Western and Eastern Canada. But then we can kind of go a little bit further to do some more validations for Western Canada, where we're able to use historical events like the 2001 Nisqually and the 2012 Haida Gwaii earthquakes, as well as an AIR study that was published in 2013 to look at the impact of a Cascadia earthquake. So we've been doing some validation exercises with those using our scenario catalog. And so that's a work that's going to be published hopefully later this year. And so I just wanted to show kind of some of the results for looking at a Cascadia specific scenario. So we've seen that with the increase from Canada SHM5 to the 6th generation, that we went from about a $27 billion loss to about a $39 billion loss for the Cascadia scenario. Once again, we're only looking at the ground up building losses in this case. And on the right-hand side, showing some of the other metrics that we're able to look at with our model. So in this case, looking at the number of different casualties of varying levels of severity, from those requiring only a basic first aid to those who unfortunately would be killed instantly, and looking at the spatial distribution. And then I also wanted to quickly touch on some of the things that are specific to Western Canada that we kind of have on our radar that we're working towards for the next iteration. So things like implementing the basin functionality in NGA West. So we're already using those ground motion prediction equations, but maybe not yet fully utilizing the ability to look at basins. So that's obviously a high priority for the Vancouver region, with keeping in mind that as a national entity, we have to think about our ability to cover with the same level of resolution the entire country. Another thing, we're engaging in a study with the Global Earthquake Model Foundation to do some tectonic block modeling. So similar to some of the other groups here, where we're using GPS velocities to look at active faults in the Lower Mainland region, because we know that we have a much better idea of what they look like south of the border than we do north of the border. And then also using a USGS ground failure code to look at liquefaction and landslide. So not necessarily the susceptibility, but for our scenario catalog, running the co-seismic kind of forecasting of where we believe that liquefaction landslide would occur. And so we've done a validation study for that with a student of mine looking at Haida Gwaii. And then finally working with some UBC collaborators, as I've mentioned before, to think about our BC specific construction. And so hoping to make some updates to the fragility and vulnerability functions for the next iteration of our model.
Thank you for that, Tegan. So in the interest of time, we'll keep going. Paul, so next slide. Okay, so basically we're going to do a repeat, but look at Eastern Canada. And in the interest of time, I'm just going to say in Eastern Canada, we're trying to do a similar thing as to we're doing in the West, but there's some added uncertainties due to, as mentioned by some of the other speakers, while large earthquakes have occurred, such as the 1663 Charlevoix earthquake or the 1732 earthquake near Montreal, which have been relatively close to urban centers. The rate of these earthquakes is lower than in the Western Canada, and so there are higher uncertainties associated with characterizing risk and hazard in Eastern Canada. And this poses a unique challenge. One of the recent developments we've seen in Eastern Canada is the release of the NGA East ground motion models. These are the next generation in ground motion models for Central and Eastern North America. And some of the panelists will talk about that a bit further in the next slides. And I'd ask the panelists to try and keep it to just the key main topics to try and keep us on track for the next session. Thanks. Next slide, Paul.
Thanks, Michael. So as Michael explained, when we turn east, we see the lack of ground motion recording across magnitude and rupture distance where we actually need it. The frequency variations between the crustal and stable continental tectonic regimes come into picture. For example, an event of magnitude 7 as shown on the left-hand side figure, and if you take a location at class C, and a location near Quebec in Eastern Canada would produce almost similar level of ground shaking, next please, from a magnitude 8.5 to 9 megatrust event that happens in Western Canada. So we also observed the low-rise buildings shown by the blue colors here are having a higher contribution in both West and East. So I wanted to make sure that we understand that East and West we're dealing with different animals, but at the same time, the seismicity and active tectonic regimes are actually playing an important role. Another thing we observe is the large epistemic uncertainty or model-to-model variability among the Eastern models, including the NGA East. So NRCan 6 hazard increase in East is mainly driven by NGA East ground motion and site response model updates. So given that we already included the preliminary NGA East models and a forward-looking site implication model in RMS model, even though you go from NRCan 5 to NRCan 6, there's a larger hazard increase. Going from RMS Canada earthquake model to NRCan 6 would have much smaller impact in the loss. So we communicated our view in this blog that we have, next please. In fact, we did a loss impact study in US incorporating the 2018 USGS hazard updates that includes the NGE studies. And if you're interested, you can also contact us about that. Next please. Next, please. The most active region in Eastern Canada is the Charlevoix seismic zone. And the seismicity in the St. Lawrence River becomes really important because it's quite different from the seismicity outside of this region. It's also co-located with some of the Canada's oldest and high exposure cities. Next, please. Because the St. Lawrence Rift region has concentrated the population that goes back much further in time than other parts of the Eastern Canada. This actually means that we expect that the earthquake catalog in this area to be more complete, or let's say it's more trustworthy further back in time. So therefore, it's treated carefully and separately from the rest of the Eastern Canada catalog. Next, please. St. Lawrence River has also importance not only from a seismicity perspective, but also from a geotechnical and site effects impact. We collected pretty dense amount of number of VS30 measurements, shear wave velocity measurements, and you can see them by the little dots around the Ottawa area. And this map is on the right showing the RMS high resolution geology based VS30 map. Red colors indicate the softer, more vulnerable soils, which actually dominate this rift, as you can see around the Montreal area. So this extensive soft soil clay from the older marine deposits from an ancient inland sea, it was called Champlain Sea, are actually responsible from this associated with the higher ground shaking. Thank you very much.
Thanks. Could you go to the next slide? Yeah, so what we heard from other presenters and NRCan's publication is really that Eastern Canada is characterized by lack of data and a lot of uncertainty. I'm not going to get into the detail of that. Could you go to the next slide then? Therefore, are really key to modeling areas that are characterized and subject to large uncertainties to account for different possibilities and bring in all the different models that exist in this area and then blend them together. And our approach has been exactly the same. We use a logic tree both for the source models and for ground motion models. What you're seeing on the top figures are the source models that we have used in our model. That it's a combination of the historical model that assumes events are basically happening in clusters in the locations of the previous events. And then there is the regional model that considers events can happen in a wider area in the seismotectonic similar area. So we combine those two and also account for possibility, the smooth seismicity, which is the model that USGS adopts. And then with respect to the ground motion, again, as you heard, it's very important to consider a variation. This is an area that individual ground motion models can be very, very different. And our approach has been to, again, use a weighted average, account for both aleatory and epistemic uncertainty explicitly through the ground motion models. And this is done by using also the VS30s and site amplification within each ground motion model. And that's what sixth generation model has done. Next slide, please. So when we look at the changes from fifth generation to sixth generation, what we observe is that the primary cause of the increase is on how uncertainty is treated. Moving from the previous approach of representative suit to use of the classic logic tree, and then incorporating the uncertainty within the GMM. And that's exactly the methodology that we have used in our US-Canada combined model. So from that uncertainty aspect, we do not expect the differences be significant. However, we have not used the NGA East equations in our ground motion model. So that's some area that we are looking into to incorporate when we have a new future update. However, the impact is not very clear. It depends on magnitude and distance. In some locations, comparing NGA East with what we have might increase, in some places might decrease. And that's even more complicated if we want to look at the loss changes, which is very much dependent on exposure type and their location. Thanks. I'll turn it over to the next presenter.
Next slide, please. So I think we've established that with East Canada, a key item is capturing uncertainty. Let's start my timer there. So it's a wider area of large population affected by lower hazard typically compared to the West. But the key again is in capturing the uncertainty. So the main changes from 5th to 6th gen, I think we've heard it a couple of times, but they come from a change in how we capture the attenuation of stable shallow crust events. And that is a logic tree has been applied to cater for aleatory uncertainty, and a new NGA East ground motion model is applied with a 50% weight, which is more assimilation based. So I've produced the EP curve that I did for West Canada here because I wanted to know, given that the main changes are to stable shallow crusts, I just wanted to make sure how much of the risk across the tail, at the AAL, etc., is coming from this seismic source. And when we look at the seismic sources that drive the losses in East Canada, right from the AAL to the 1,000 year over 10 period, and this is again talking about insurance loss here, the picture is quite simple. It's all virtually driven by the stable shallow crust type seismic events. So if we think back to the triangles in Michael's map, we see large areas of Eastern Canada that have in excess sometimes of 100% increases in hazard. So in terms of capturing the uncertainty by applying the logic tree in the GMMs, CoreLogic already does that in our Canada quake model, but there will be a change when we adopt the NGA East GMM model into our CAT model. And as we can see from the EP curve here, the losses from AAL right out into the tail are highly sensitive in east of Canada to any changes from to stable shallow crust events and how we capture those events in terms of ground motions. So we can potentially see large percentage changes across the EP curve. But percentage increases is probably the key word here. Outside of the higher seismic regions of Eastern Canada, areas of Montreal, typically northeast, especially northeast of Quebec City, these changes could go from low to less low. And in terms of insurance, so in terms of human safety, of course, we go to a higher return period, but in terms of the 500-year and insurance focus, and especially given 15% or less maybe, but high earthquake deductibles, typically the insurance industry is more safe, shall we say, from these lower ground motions. If we go to the next slide. For my last slide, and I've cheated here, I've gone back to West and East Canada, and this is a very approximation analysis. So I don't have time to go into all of the caveats in this, but this slide is only good for what I'm going to point out for. So looking at the 500-year return period hazard and a rough guide of cumulative population that is subject to hazard on the 5th gen. And then we have spikes that we can see in the 6th gen, which actually just counts as uncertainty bands. So I'd see the light green shades here as essentially uncertainty and variation in what could increase. So the main things I just want to point out is despite percentage changes in the hazard being different in different areas and seeing higher percentage differences and increases in the east, the areas of higher hazard do indeed remain higher hazard. So if we take the left of this map here, we can see the highest hazard areas are on the left. So we can see a big dip after around 100,000 population, which would most likely be most of Victoria. Then we can go to see Vancouver, another 700,000 or so. And also locations typically northeast of Quebec City will be hidden in here. And then we get into a slow slope gradient, shall we say, beyond the 2.5 million potentially. And we can see the impacts of the increases here in spikes. Again, this is kind of a worst case, best case scenario. That's why they're spikes. And oftentimes this is tied to softer soil conditions. So not many buildings are built on these softer soil conditions, but the change in the treatment of the GMMs that we've all been discussing, it tends to increase hazard the most on softer soils the most. So from a risk perspective, locations on softer soils have even higher hazard increases. This could translate into higher gradient of risk over smaller areas than we've seen potentially in the previous version of the model, and due to the varying soil conditions and treatment. And then my last, a bit over time, but lastly, there's a natural cusp of hazard where we expect to see damage in earthquake modeling and the potential for large changes. On a straight 5th to 6th gen NRCan model, we may see large changes in ground up average annual loss due to the increased hazard. But when it comes to actually I might have mentioned this, the earthquake insurance deductibles, I just want to hit that home. This does tend to take a lot out of this issue when we talk about lower hazard, especially if the earthquake deductibles are quite high. And I'm going to stop there, and apologies for going slightly over time.
Okay, so you can go ahead to the next slide. So once again, our implementation is as close as could possibly be to the inherent NRCan hazard model. So of course, as it's been mentioned already several times, I don't want to belabor the point. The biggest change here is going to be for the ground motion prediction equations and the treatment of uncertainty. We were generally going from in the 5th generation model, 3 representative equations with their uncertainty, and now we have quite a suite. I think there are 13 ground motion prediction equations, all within the NGA East suite. So the uncertainty is much larger, and that's obviously going to affect our risk. One of the other big contributors to the risk that I have been noticing in Eastern Canada that I wanted to touch on. So what I'm showing here is some of that validation work that I mentioned before. So here, trying to do as much as possible a one-to-one validation with the AIR 2013 study that was just a bit of background. It was commissioned by the Insurance Bureau of Canada to look at the impact of a catastrophic event in Western and Eastern Canada. And so on the left-hand side, I'm showing the resulting ground shaking from that eastern scenario. So this is a Charlevoix earthquake, a magnitude 7.1, using a set of GMPEs that were selected by AIR. And on the right-hand side, reproducing the same thing using the same GMPEs, but with the Canadian model. So I'm not actually talking about any of the GMPEs that are in the 5th and 6th gen necessarily. This was just to point out another kind of big difference for Eastern Canada, is that we believe that there's quite a difference in terms of some of the other elements of the model that could be related to the exposure model or perhaps the vulnerability and fragility functions used. Because you can see that while they're colored the same, it's not so easy to compare the two maps, but generally speaking, we see that the hazard is mostly consistent. And so if we've made the hazard consistent and then said, how does our overall risk look between these two different models? And again, it's an outdated version of AIR's model. You can see on the bottom there in that little chart, I'm showing the results both for Cascadia and for Charlevoix. So the Cascadia models kind of line up at about $43 or $33 billion in loss for a Cascadia scenario, but for the Charlevoix scenario, AIR predicted about 40 billion in loss, and we predicted about, I think the models range between about 7 and 9 billion. So we think that there might be some other major changes that are specific to Eastern Canada, likely perhaps related to the building stock and the kind of fragility vulnerability functions that are being used there. So I think that's, again, something that we're looking at as we go forward with our Eastern Canada. Thank you.
So thanks to all of the panelists for going through that. And so, encourage the panelists to look at some of the Q&A questions that came in and perhaps respond to some answers or follow up on them. And thank you very much to everybody. And I'm going to hand the reins over back to Paul.
Michael, thank you for putting together the session today. That was really informative. Lots of information there. And thanks to everybody for participating. I wish we had more time for conversation, but we covered a lot of ground and shared a lot of information. So thank you all for your efforts there.